Going to talk about solids and liquids absorbing heat. We'll talk focus issue. Come on now. Is that going to focus? There we go. So we'll talk about gases more later, but for now I want to focus on solids and liquids, in particular the terms specific heat, heat capacity, and latent heat, sometimes called specific latent heat. I always call it latent heat. So let's just get that out of there. All right, so by definition, lowercase c, that's a lowercase, is called specific heat. It's defined in this way. It's the derivative, not with respect to time, but with respect to temperature. So lowercase t is time, capital T will be temperature in these problems. It's 1 over the mass times dq dt. So what does that really mean? It's the amount of heat required to raise 1 kilogram of a material by a temperature change of 1 Kelvin. And because the increments of Kelvin and Celsius are equivalent, and because we're talking about changes, I can also be talking about per degree Celsius. To be clear, 30 degrees Celsius is not the same as 30 Kelvin, but a change of 30 degrees Celsius is the same as a change of 30 Kelvin. All right? Heat capacity is capital C. All right, which is oftentimes thought of as lowercase m times lowercase c if you have an object that's made of all the same material. If an object is made of different materials, you can't use this. If an object is made of different materials, it's just big C. But that's basically, you raise the temperature of the object by 1 Kelvin, and it corresponds to the heat required. So if we look at these in equations, the famous equation is usually Q equals mc delta T, where this is lowercase c, whereas the equation that corresponds to this one is Q equals capital C delta T. So if you have an object, you could use heat capacity. If you have a material, usually we use specific heat. And then something I might mention about this, if you have a very large temperature change, sometimes the amount of heat does not scale linearly. So this is an approximation. And I think I address what happens if the approximation is not valid in one workbook question. That said, for most problems in most physics classes, we usually assume that C is a constant over a huge temperature range, even though that's not always true. This will get you approximately the right value. So if you know the mass and the material, so you could look this up in a table, and the temperature change you need, this tells you how much heat you need to raise the temperature of your material. Okay, now some things get a little bit trickier, such as ice, right? When you melt ice, you don't see the temperature change because you get this ice-water mix. So we'll get an equation for, that's an example of a latent heat of fusion. Latent means hidden. And I'm gonna, in this case, mean hidden delta T. There's no delta T in a phase change. At least when we're talking about one of these phase changes. All right, so if we're talking about solid going to a liquid, we're talking about latent heat of fusion. If we're talking about a liquid going to a gas, that's a latent heat of vaporization. And sublimation would be going, say, from solid directly to gas. The equation that governs this one is Q is equal to plus or minus latent heat of fusion. This one would be M, latent heat of vaporization, and this could be M, latent heat of sublimation. And there's always this plus or minus. So what does this mean? If you're melting something, you could look up in a table the latent heat of fusion for, say, ice, the ice to water transition. This is a number you could look up. You multiply by the mass of ice you have, and that tells you how much heat is required to melt that ice. If you have some water at 0 degrees Celsius, I should be careful. For all these, for these processes to occur, you want to be at the critical temperature. For example, if you want to talk about freezing water or melting ice, first you use this equation to figure out how much temperature is required to get it to the melting point or the freezing point. So you use this equation as you're changing temperature to get the thing to the melting point or freezing point. Then you use this equation to try and learn about, okay, how much energy to melt or freeze it, and then you could keep going. So for example, and I'll do some examples in a minute, and why don't we just leave it at that for right now? We'll do examples in the next video.